Okay, this one's actually kind of fun. I think all of these are fun, so I can't actually look too crazy. But the statement is that a circular wire loop, radius r with resistance big R, encloses a region of uniform magnetic field B perpendicular to its plane. The field occupying the shaded region of the diagram increases linearly with time, so B is equal to alpha T, and an ideal voltmeter, infinite internal resistance, is connected between the points P and Q. Okay, what is the current in the loop, and what does the voltmeter read? So again, we're seeing here that resistance is a function of geometry, which we saw earlier from Ohm's law. And this geometry is actually pretty cool. So we have some loop, which appears to be on a sphere. So that horizontal line that has the V in it on a diagram, that's a loop. And we've seen this before as we're coming down in several diagrams. And we see that R from the center is, we're looking at point P and Q, and their angle in between forms 90 degrees. All right, so we're on the same horizontal surface, and that's what tells us that the radius angles make 90 degrees. All right, so this geometry will come into effect, so let's be careful with it. All right. So use the EMF in Lenz's law. So what we need to do is find the flux, which is V over pi r squared. Okay. Here we got to be careful because r being a radius, we need to be careful where it is with respect to P and Q. But it's pretty straightforward. We saw that B was equal to alpha T. So here we have that the EMF is equal to negative pi r squared alpha. V equal IR tells us that I is equal to V over R, or the EMF over R, so we are equal to pi r squared alpha in magnitude. But if B is out of the page, Lenz's law says that current is clockwise. So again, be careful there. So B inside the shaded region for a circle of radius S, apply the Faraday's law. Okay. So again, it doesn't really matter what the radius is for the flux. We're all going to pass through it. Just be mindful that it does matter when we're dealing with things inside the region. All right, so hence the circle of radius S. So what this tells us is that the closed line integral is equal to negative time derivative of the flux. And we see that the integral yields to e 2 pi s, and the flux is equal to negative pi s squared alpha. So you see that a factor of pi and s cancel, and we're left with E is equal to negative alpha s over 2 phi hat. Convert this to Cartesian for convenience. And now you see that s, on the horizontal surface, that's equal to cosine phi in the x direction and it's negative sine phi in the x direction and cosine phi in the y direction. Okay, so that's what they're representing. If we substitute in the definition for sine and cosine, we get y over s, and then for cosine you get x over s, so the s factors cancel and the negatives cancel as well. And then along the line from P to Q, we see that dl is equal to dx x hat, and y is equal to r over root 2, and this is where the geometry comes in. Y is equal to, if we draw this as a triangle with r being the hypotenuse, then you see that the two legs of it will have to sum together, and that's where we get x squared plus y squared, all that fun stuff. That's where we get that, we get 2y squared equals r, so take the square root of both, and then you get square root of 2y equals r, and that's how you get y equals r over square root of 2. So use your geometry. The 90 degrees saves you a lot when trying to set up a similar triangle. Just FYI. So V, which is the line integral of E, we can now run through. Okay. So since alpha over 2 is a constant, shove it on through. What we want to do now is write everything in terms of dx. So we're pretty easy to do there. Again, since it's only in the x direction that we're interested in, the y hat term doesn't matter, but we saw that y was equal to r over root 2. But note that we're running, if we set one of the points equal to 0, then we have to double the distance of r. So that's where we get root 2 times r. So we're going from 0 to x, which again from the triangle is equal to, from the triangle is equal to root 2r. Again, it all comes from the triangle that is trying to hint itself in the question diagram. But yeah, so evaluate this integral, pretty easy. We just get x, evaluate it from root 2r to 0. So you just get r times root 2, and then you see the root 2's cancel, and you get r squared. And you say, thus P is at the higher voltage, okay, because in the diagram it's still left. Q is 0 point. And so the meter reads alpha r squared 2 over 2. All right, pretty easy, but again, geometry matters.